All right, hey everyone, let's go ahead and do this exam review for the final. So just remember the points are written up here so you can kind of have an idea of what to expect on the exam. I didn't add them up, but they end up being over 100 points for sure. Don't forget also you can bring that letter to a future student, and I have envelopes at the front of the class, and you just bring your letter and that will be worth 5 points as well. All right, with that being said, let's go ahead and dive into this. So the chapter 11 and 12 are worth about half of this exam, and the other half is going to be cumulative. So let's start with hex 19. So hex 19 means that the first carbon there's going to be an ine, and then we have 6 carbons in total. So 1, 2, 3, 4, 5, and I need one more, 6. Cool. All right, so let's go ahead and take this thing and react it with HCl. All right, so because it's 2 HCl, we're going to be adding a chlorine. The chlorine has to go in a geminal position, not vicinal. Geminal meaning they're on the same carbon, and it's going to go on the more substituted carbon. So we'll end up with something like this. Okay. With HBr, you'll get the exact same thing. Perfect. And it's just going to be like essentially 2 of the same reactions. The H's, by the way, were added over here. Hopefully that makes some sense. All right, if we have something like some kind of X2, so Br2 or Cl2, we're going to get vicinal and geminal. In other words, the dihalogen. So 1, 2, 3, 4, 5, 6. And then I've got, I'll have 2 chlorines on either side of the double bond. Or the triple bond, excuse me. Okay. So now we get into some interesting parts. So if you remember, when you have a terminal, you need it to add a terminal alkyne, you need it to add mercury in order to get this reaction to occur. And what happens is we add an alcohol to the alkyne. So, and in this situation, it's going to be at the most substituted position. So we would technically get the alcohol there. If you remember, this thing would tautomerize into the more stable ketone position, and that would be your final answer. Okay, so this is really what we're looking for. But this would be kind of an interesting intermediate that is also still present in the final solution. If you remember when we use boron, that is something magical and special in H2O2 and water, or H2O2 and OH minus. Normally you could use BH3, but because it's terminal, you're going to have to use this R2BH stuff. So what that does is it places the alcohol in the least substituted. So I mean, you'll get a very similar product as you did last time. The double bond's in the same spot, but this time we'll have an alcohol on the primary carbon. This again will tautomerize, and we'll be left with what we call an aldehyde. Many times you'll write the H here just to put a stamp on it, the fact that this is an ending aldehyde. All right, this is a fun one. If we take this thing and we react it with NaH, in other words, just H minus, this is a strong enough base right here that it can grab this thing right here, the hydrogen right here, and these electrons can go on there. And if you remember, when we use NaH with oxygen, we make a nucleophile. The same thing when we use an alkyne, we make a nucleophile. So you'll get essentially the same thing back, just without that H now. And this would be a negatively charged thing. All right, in G, it's saying, hey, first make it a nucleophile. So this is the exact same thing. An H2 negative will actually do a very similar thing as just the H minus. And so we'll get the nucleophile from this. So this one will give us the nucleophile with a negative charge. This is a negative charge, not a methyl group or anything like that. Okay, so this will now react with this ethyl bromide, we'll just have a straight up SN2 reaction. That pops there, that goes there. And what you're left with now, I'm just going to kind of draw the same thing I had before. But now we'll have an ethane group on this side, or an ethyl group, like that. All right, the same kind of thing can happen for epoxides, and we'll actually run into this reaction here in a little bit when we talk about synthesis. Epoxides are really helpful in synthesis. So if we first, after 1, do this, we know that we get this nucleophile. 2, let's go ahead and react that with a 1 to epoxide. So simply this. This is going to attack either side, doesn't matter. It would normally attack the less substituted side, and that's going to go up there and pop up there, and we're going to get, I'm going to kind of flip this thing around a little bit, if that's okay. But we will end up with, we'll put the oxygen up here. Okay. And then after that oxygen, we will now have the triple bond. Okay. And then 1, 2, 3, 4 more carbons. So 1. Let's make sure our carbons are correct. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Perfect. And then we have the epoxide. Perfect. No, it's not perfect. Should have done this in, well, I can't do it in pen, you guys can't see it. 1, 2, 3, 4, 5, 6. So that gives us this, and then we still had the 1, 2. So it's actually doom, doom, and that's where the oxygen is gonna go. Okay. And now when we follow it up with water, what happens, just to remind y'all, this is kind of an older reaction, is that grabs the H, that goes there, and you end up with an alcohol. So we will get something like that. All right. Yeah, I wonder, I think I might have missed a carbon in the review thing, in the key. Okay. You know, just chapter 12 reactions. Chapter 12 reactions, a lot of them were relatively straightforward. The reductions were relatively straightforward. And just to remind you, if we had like an alkane, or excuse me, an alkyne, and we reacted it with H2 and PDC, we got the alkane. Right? If you reacted it with H2 and Lindlar, you got the cis product. And it was only strong enough to take it to an alkene. It could not react an alkene, right? And if you did the, with the sodium and the NH3, excess of these, you would get the trans product. Okay? And it was only strong enough to do the alkyne. It could not break up an alkene and reduce an alkene. All right, with that being said, that will hopefully help us get through some of these. So let's start it off. It says we're reacting cyclopentene. In other words, that. So in the first one, if we react it with this, we should expect to get the alkane. We know that H2 and PDC is strong enough to take an alkyne all the way to an alkene and then an alkane. All right, in B, however, we know that a Lindlar catalyst can take an alkyne to an alkene, but it cannot take an alkene anywhere. So this will have no reaction. It can only reduce alkynes. And the exact same thing you'll encounter here. Na and NH3, it can't break up this alkene. It's not strong enough, so you'll get the exact same answer. It can only reduce alkynes. As we move on to oxidation reactions in chapter 12, when we see this thing, we know that this reacts to give us a beautiful epoxide. So we can take an alkene and turn to epoxide. In E, you're essentially taking that epoxide and then doing some more reactions. So let's do them. So we would first have this epoxide, right, for 1. And then in 2, H2OH and OH minus, the OH minus can act as a nucleophile. It's going to attack, moving that up. But it's important to note that this would occur in anti-fashion. Hold on, I gotta be... Okay, sorry, I'm back. So we'd get this in anti-position, and nothing is saying that it wouldn't also be this. All right, for the next one, we are once again here. This we know helps add alcohol, and this creates a diol. So the diol that we're going to get is going to be in syn fashion though, because if you remember, the OSO4 kind of goes on there at once. The 2 oxygens kind of attach all at the same time. And so that's why you'll get a syn fashion. Nothing's dictating whether it's going to be a wedge or a dash. So we'll do both products. In the next one, we get the same thing. KMNO4 acts a lot like OSO4. If you remember, it's just less expensive. And so we'll get the same product, both in syn. All right, last but not least, just to make sure, because all these things can start to kind of mix in your head, right? We have this. Do you remember in this situation, the H acts like a nucleophile, but there is no partially positive site on this thing for it to act as a nucleophile, right? So there's no reason for these electrons to go attack an already electron-dense site. So for this case, there's no reaction. If you remember, we do use them. We use them for epoxides and alkyl halides. So for example, if you had, I don't know, this, and you're reacting it with this. So if you have something primary or secondary, you'll get an SN2 reaction, which would just be that, which I don't really like drawing. Let's add another thing to that just to make it more reasonable, because we wouldn't draw the H right at the end of the day. This also would work for epoxides. If you remember, kind of breaks them up. If you follow it up with water, you can make an alcohol. So let's do it because we can. So let's say you have an epoxide and you react it, and this would have a negative charge, by the way, I didn't draw it. H, ALH3 negative, and then you follow it up with water. So 1, 2. You're going to break this up, and the H will go to the less substituted position. So if there happens to be a methyl group on there, then it's going to go to the less substitute. Hold on, I got somebody. Okay, I'm back. So you're going to have the less, the H will add to the less substituted position, and when you follow it up with water, it can grab that proton. So you'll end up with something like that, and you would also get it's an enantiomer. All right, moving on. Ooh. This one's got to be one of the cooler reactions of the semester, I think. So when we have that dimethyl sulfide, and we react it with the ozone, dimethyl sulfide, remember you're going to break that bond there. So you're essentially going to have a pentane, right? but at the end of each pentane, you'll have double bonded oxygen. So 1, 2, 3, 4, 5, just make sure we're good. That would be an O. That would be an O. These are aldehydes, so you might want to consider putting the hydrogen on there, just so you don't confuse anyone. But if you left them off, that's just fine. All right, this next reaction is no. Nope, didn't do it. It's a very specialized thing, and we don't need to do it. So we're going to move on to K. So in K, this is something that's really important for synthesis. Because it can take a double bond and it can make it an epoxide. And that you're going to use quite frequently in synthesis, okay? In fact, I'll show you in just a second how frequently we'll use it. Okay, and this one it says, now take this product and react it with this, in which case we have now a nucleophile that's an H minus and then water. As we did previously, you just get an alcohol at the least substitute, or the alcohol will end up at the most substituted position. The hydrogen will come in here, but just to remind you what's happening, because it never hurts to practice, that thing's going there and that's popping up there. And then when we follow it up with water, in fact, let's do it step by step, because I realized I don't think in class, somebody asked me after class what happened, and I think that's probably pretty important to go over then. So the hydrogen was added here. We don't need to draw it, but when you follow it up with water, OH, I could put, probably ought to put, let's draw that again. This is going to grab that, this is negative charge by the way, and that goes on there, okay, and that's how you get the alcohol. All right, moving on. All right, it wants to make this thing from 4-bromo-but-1-ene. So first let's draw 4-bromo-but-1-ene. So we've got the butane, at the 1 we have an ene, and at the 4 we have a bromine. All right, and we want to make this thing, like what happened? But when you sit and think about it for a little bit, it's not so bad. We know that this is an attack site right here, right? So something from over here is probably going to attack over here, and it looks like there's an oxygen in between it. So we need to somehow put an oxygen here that can attack over here. We've done something like that before, but we've made it, if you remember, we used NaH and made it O negative, and then it can attack there. But if that attacks over here, so that brings us here, was the oxygen, there's also, on the carbon next to that, an alcohol. So we got to learn how we're going to get an alcohol on there. So we have an O negative and somehow an alcohol here, okay? There are several different ways we could do it. And we could do, for example, the potassium permanganate, the MnO4, or the OSO4. That will add 2 alcohols to this. Or we can always, when in doubt, try an epoxide out too. Hi, I like that. When in doubt, try an epoxide out. So let's do that. Let's do an epoxide just because I like epoxides and I think they're more useful for synthesis. So MCPVA. And what that's going to do is that will give us that epoxide we wanted. Okay. Now we have an oxygen. We can go ahead and add like an alcohol as a nucleophile, and that will pop one of these up. So if we add alcohol as a nucleophile and follow it up with H+, now we have an alcohol, right, on both spots. In this situation, they'd be anti. But it doesn't matter. At the end, our end product doesn't have any stereogenic centers. Okay, so now we're sitting kind of pretty. We have an alcohol, we have an alcohol. This is this alcohol, if you can see it. And if we can get this oxygen to go over here to this site right here, we will have this molecule. So let's see if we can do it. In order to get this alcohol to be a nucleophile or be able to attack this bromide. Let's use NaH. And when we use NaH, although you'd have several different products because nothing is stopping the this alcohol from becoming a nucleophile as well. But that's the beautiful thing about chemical synthesis. You just kind of do what you want. That sucker would pop over there, that would pop over there, and you get that. So when in doubt, epoxide it out. And let's do another one. There's another synthesis question. It says design this. Right away I see this alkyne thing. And hopefully you're like me, you recognize this and you're like, oh yeah, that had to have been, like maybe there was a H to a carbon, triple bond it to a carbon, to an H, and you ran it through with some NaH. The H minus took off this H and it made a nucleophile. Which would be this part right here. So this thing is going to attack something somewhere, right? So we want this to attack. We also want an O double bonded on there. We don't know how to directly put an O double bonded onto this while still leaving this site open, but we do know how to put an alcohol, and we know how to take an alcohol and then oxidize it into a double bonded O, into this ketone that you have here. So let's go ahead and do what we know. When in doubt, epoxide it out. Let's start with an epoxide, because if we start with epoxide, we know we can add two things to either side of the double bond quite easily. So let's go ahead and start with this. We would need the MCPVA, and you would get the epoxide. Okay, from there, you know you can just attack with a strong nuke. And that's what we have. They have this nice, strong linear nucleophile here that should be negatively charged. So let's attack this with the CH negative. And so that would attack there, popping that up there. And we'd have this beautiful thing. That. And now we'd have to follow it up with water. You could have also put the water in this step right here. It's pretty common to do, to just do a two-stepper. And that gives us the alcohol. And now you have a secondary alcohol, which we know we can oxidize into a double bond simply using PCC. We're done. Okay. And I'm sure there are many, many other ways. You could have done an OH minus. You could have done Br. You'd done Br2 and water, and would have added a bromine and alcohol. There's lots of things that you could have done. And then with that bromine, you could have then attacked with this as a nucleophile, done an SN2, and then done the PCC. There's very, very, very many ways that you could do this, but that was just what came. So, all right, draw resonance structures for this thing. Okay, so when you're drawing all the resonance structures, it really helps to go slowly and maybe do one thing at a time. So the first thing I think of is maybe that bond goes there, because I have a positive charge and I have a negative. And remember, anytime you have like some kind of positive or negative, the negative will move to the area of the positive. So let's start there. I could not have brought this down here because I would have then had 5 bonds to carbon, if that makes sense, and you can't do that. So our first step will be what we did. So we have this going to a carbon. We now have a single bond to an oxygen. We have the CH3, and we still have this oxygen that's negatively charged. But the difference is, because this carbon lost its bond, it now has a positive charge. Now, those electrons can go down there. And now you can have this, where you have a double bond to the oxygen O to a CH3. And those are the main ones that I think I would look for on an exam. So just always follow areas of high electron density and move it to the areas of lower electron density. Okay, circle and label functional groups. Yes, this is an amine, but the bigger one right here is an amide. Here we have an ether. This is an aromatic. And there's not much to do here except for memorize these. Here we have an alcohol, specifically secondary. Here we have a secondary amine. And I think that about covers it. But yeah, definitely you will want to know functional groups, especially as we continue on into organic chemistry too. Okay, chair conformers. So there's no question here. I didn't actually ask you a question, but just let's kind of remind you of what they are. So before I do, after last exam, we talked about, by last exam I mean after the exam where we went over chair conformers, we talked about the fact that fluorine is bulkier than CH3, which is bulkier than chlorine, which is bulkier, or bromine, which is less bulky, I should say, than bromine, which is less bulky than iodine, less bulky than an ethyl group, which is less bulky than an isopropyl group. So these are kind of the common things that you'll run into in terms of bulkiness that are on chair conformers. If you remember, the most bulky on an equatorial position is going to be more stable. Okay, so the more bulky on an equatorial position is going to be more stable. So for example, if we have something like this, put the Cl there. And here, if this thing's down low, and I'm going to put a bromine right here. And you should remember that everything pointed up has a straight up arrow with a hydrogen on it or something, a substituent on it, and everything pointed down has the down. Now when we flip this thing, which looks beautiful by the way, this is 1 and this is 2, this is now 1 and that's 2. Okay. So what was up stays up, but if it was axial, it becomes equatorial. So that means this 1 right here is now that one. What was up stays up, but what was axial becomes equatorial. And what was equatorial becomes axial. So you'll end up with something like that. And if I asked you which one is more stable, or show me the direction of the equilibrium, etc., because these two things would be in equilibrium, hopefully they agree the more bulky thing is bromine. And bromine is going to be more stable when bromine is on the equatorial position, meaning right here. So the equilibrium would yield that way. Okay, moving on.